How does a computer predict how a structure will deform? The answer begins with a remarkably simple idea. In this tutorial, we will build finite element analysis from scratch using one straight axial bar. By the end, we will go from the physical bar, to finite elements, to a global stiffness matrix, and finally to displacement, strain, and stress. Let's begin with a simple structural problem. We have a 2-meter-long steel bar, with a cross-sectional area of 100 square millimeters and a Young's modulus of 200 gigapascals. The left end is fixed, and a 10 kilonewton tensile force is applied at the right end. Our objective is straightforward: find how much the right end moves, and determine the stress in the bar. Finite element analysis does not try to solve a complicated structure as one giant mathematical object. Instead, we divide the structure into many smaller pieces. These pieces are called finite elements. For our demonstration, we will divide the 2-meter bar into 2 equal finite elements. That gives us 3 nodes: node 1, node 2, and node 3. Each element connects 2 neighboring nodes. The next question is, what do we actually calculate at each node? For this one-dimensional axial problem, we only need the displacement along the bar. We therefore have 3 displacement degrees of freedom: U1, U2, and U3. These unknown displacements are what the finite element equations will eventually determine. Now we need a relationship between force and displacement for one element. In basic mechanics, we write force equals stiffness times displacement. In finite element analysis, the same idea becomes a matrix equation. For a 2-node axial bar, the element stiffness matrix is given by this expression. For our bar, the area is 100 square millimeters, the Young's modulus is 200 gigapascals, and each element is 1 meter long. Therefore, the coefficient AE over L is 20 million newtons per meter. Now we reach the heart of finite element analysis: assembly. Each element has its own stiffness matrix. Because element 1 connects nodes 1 and 2, and element 2 connects nodes 2 and 3, we place their contributions into the appropriate positions of one global matrix. Notice the 2 in the center of the matrix. It appears because node 2 belongs to both elements. This assembled matrix now represents the stiffness of the entire bar. The global matrix alone is not enough. We must also tell the mathematical model how the structure is supported. The left end is fixed, so the displacement at node 1 is 0. This is our essential boundary condition. It removes the rigid body motion and gives the structure a physically meaningful solution. We now have the standard finite element equation: global stiffness times the unknown displacement vector equals the applied force vector. After applying the fixed end condition, only U2 and U3 remain unknown. Solving this small system gives 0 displacement at the fixed node, ½ millimeter at the middle node, and 1 millimeter at the loaded end. Displacement is not our final answer. Once the nodal displacements are known, we can calculate strain inside each element. For a linear axial element, strain is the change in displacement divided by the element length. Then Hooke's law gives the stress. For this example, the strain is 5 times 10 to the minus 4, and the resulting stress is 100 megapascals. A good engineering calculation should always be checked. For a uniform axial bar, we already know the classical solution: the tip displacement is FL divided by AE. Using the same physical parameters gives a displacement of exactly 1 millimeter. Our finite element solution is also 1 millimeter. The numerical and analytical solutions agree, with essentially 0 error for this simple problem. Let's summarize the entire process. We started with a physical structure. We divided it into finite elements, defined the nodal degrees of freedom, formed element stiffness matrices, and assembled them into one global matrix. After applying the support condition, we solved for displacement, and then calculated strain and stress. But there is an important question we have not answered yet. What happens if we use one element, 4 elements, 8 elements, or 16 elements? And how do we know when the finite element solution has become accurate enough? That leads us to mesh refinement and convergence. We know that finite element analysis divides a structure into smaller elements. But a practical question immediately appears: how many elements do we actually need? Should we always use more elements? In this tutorial, we will investigate mesh refinement and one of the most important ideas in finite element analysis, convergence. Let's return to the bar from tutorial 1. The geometry, material, loading, and boundary condition are exactly the same. The analytical tip displacement is 1 mm. This time, however, we will solve exactly the same physical problem with different mesh densities. Suppose we use only one finite element. There are 2 nodes, one at each end of the bar. We solve the finite element equations and obtain a tip displacement of 1 mm. That may seem surprising. We have used the coarsest possible mesh, yet the answer is already exact. Now let's refine the mesh. We divide the same physical bar into 2 elements, then 4, and finally 8. Notice what changes: the number of elements and nodes. Notice what does not change: the physical bar itself. Mesh refinement simply gives our mathematical model more locations at which the displacement can be represented. Now let's compare the numerical results. We solved the same bar using 1, 2, 4, 8, 16, and 32 elements. Look carefully at the tip displacement. It remains 1 mm for every mesh. The error is essentially 0. The reason is mathematical. For a uniform axial bar with no distributed load, the governing equation gives a linear displacement field. And our 2-node linear bar element also assumes a linear displacement field inside the element. So the finite element approximation can represent the exact solution perfectly, even with one element. So why do engineers usually perform mesh refinement? Because real structures are rarely as simple as our uniform bar. Consider a plate containing a hole. The stress field changes rapidly around the hole. A coarse mesh may not have enough resolution to represent that variation accurately. A refined mesh provides more resolution where the engineering quantity changes rapidly. A convergence study means that we systematically refine the mesh and monitor a quantity that matters to us. Here we monitor the tip displacement. For our uniform bar, every calculated point lies on the exact solution. The curve is therefore flat. In a more complicated problem, these points would generally approach a stable value as the mesh becomes finer. That behavior is what we call convergence. In practice, we need a criterion for deciding when the mesh is sufficiently refined. One simple approach is to compare the current result with the result from the previous mesh. R represents the engineering quantity we are monitoring. It could be displacement, stress, strain, or another quantity important to the analysis. If the relative change is smaller than our chosen tolerance, we can consider that quantity to have converged. For example, we might choose a 1% tolerance. So the key lesson is not that we should always use more elements. The real objective is to demonstrate that our important engineering results are sufficiently insensitive to further mesh refinement. For our simple uniform bar, one linear element was already enough. For complicated geometry and rapidly changing stress fields, mesh refinement becomes essential. In the next tutorial, we will move into 2 dimensions and analyze our first truss structure. In tutorials 1 and 2, we studied a simple one-dimensional bar loaded in tension. A one-dimensional bar is simple because each node has only one displacement degree of freedom. But real structures are made from several members, and those members can be oriented in different directions. In a two-dimensional truss, every node can move horizontally and vertically. Therefore, every node has 2 displacement degrees of freedom, ux and uy. Consider this triangular truss. Node 1 is pinned, node 2 is a roller, and a 10 kN vertical load is applied at the top node. The base is 2 meters, the height is 1.5 meters, the cross-sectional area is 100 square millimeters, and Young's modulus is 200 gigapascals. Unlike the one-dimensional bar, each node of this truss can move in 2 directions. For 3 nodes, the global displacement vector therefore contains 6 degrees of freedom. Each inclined member is still an axial bar. The new issue is that the member is not aligned with the global x direction. We describe the orientation using the angle theta and its direction cosines. The member physics is still exactly the same as the one-dimensional axial bar. Because the member is inclined, we transform that one-dimensional stiffness into the global xy system. Each of the 3 members produces its own element stiffness matrix. Assembly places each element matrix into the correct global degrees of freedom. The result is a 6 by 6 global stiffness matrix. Before solving, we must define the support conditions. At the pin, both horizontal and vertical displacement are 0. At the roller, vertical displacement is 0. Therefore U2, U3 and V3 remain as the unknown displacements. After assembly and application of the boundary conditions, the structural problem takes the familiar form Ku equals F. The constrained degrees of freedom are removed, leaving 3 unknown displacement components. The numerical solution gives the following 3 unknown displacements. The deformed shape is not guessed. It is calculated directly from the nodal displacement solution. First, the solver gives us the horizontal and vertical displacement at every node. Second, we need the original physical coordinates of those same nodes. Our coordinates are in meters, while the displayed displacements are in millimeters. Therefore, we must convert the displacement before adding it to the coordinates. The fundamental coordinate update is x prime equals x plus u, and y prime equals y plus v. For node 3, the original position is 1 meter in x and 1.5 meters in y. Because its horizontal displacement is positive, the node moves slightly to the right. Because its vertical displacement is negative, the node moves downward. This is the actual physical deformed coordinate. No magnification has been used in this calculation. Now we can visualize the deformed truss. The actual displacement is extremely small compared with the size of the structure. For node 3, the displacement magnitude is only about 0.780 millimeters. If we drew that deformation without magnification, it would be almost impossible to see. Therefore, the displayed deformation is multiplied by 1500 only for visualization. The finite element result itself is never changed. The displacement solution is not the end of the analysis. We also need the axial force in every member. Member force comes from the member's axial deformation. Positive force represents tension, while negative force represents compression. A finite element result should never be accepted simply because a computer produced it. The two vertical reactions add to 10 kilonewtons, exactly balancing the applied load. This equilibrium check gives us an independent physical verification of the numerical solution. We have now completed our first two-dimensional finite element structural analysis. The workflow is element, transform, assemble, solve, and verify. The important point is that every step can be inspected and understood. In the next tutorial, we will derive the two-dimensional truss element stiffness matrix directly from the one-dimensional axial bar. Welcome to FEA From Scratch. In Tutorial 3, we used the two-dimensional truss stiffness matrix to analyze a structure. But we treated one important equation as a formula. Where did that matrix actually come from? In this tutorial we will derive it from first principles. We will start with the simplest axial bar, rotated into two dimensions, project the global displacements onto the member, and finally construct the complete 4x4 matrix. The goal is not to memorize this matrix. The goal is to understand why every term appears where it does. This episode is deliberately slower than the previous one. We are going to derive the formulation step by step, rather than jumping directly to the final matrix. By the end, you should be able to reconstruct the stiffness matrix from mechanics, even if you forget the final 4x4 formula. In Tutorial 3 we analyzed a triangular two-dimensional truss. Each node had two translational degrees of freedom, horizontal U and vertical V. The complete structure eventually produces the global equation Ku equals F. But before global assembly, we must know the stiffness matrix of each individual member. Let us begin with the simplest finite element, a one-dimensional axial bar. The two nodes are I and J, separated by the element length L. Because the bar carries only axial load, each node has one displacement degree of freedom along the bar axis. We call them Ui and Uj. The change in length of the bar is simply the displacement of node J relative to node I. The mechanics chain is standard. Divide deformation by length to obtain strain. Hooke's law converts strain into stress, and multiplying stress by area gives the axial force. Combining those equations gives the axial force as AE over L times the relative nodal displacement. The two end forces are equal and opposite. Writing the axial relation for both nodes gives the familiar 2x2 stiffness equation. This is the starting point. Our two-dimensional matrix will come from the same axial mechanics, but the member will no longer be aligned with the global x direction. Now rotate the same bar so that it becomes inclined relative to the global x and y axes. The physics has not changed. The member is still an axial member. Only its orientation relative to the global coordinate system has changed. Therefore, the central task is to transform global xy displacement into displacement along the member axis. To describe the member orientation, use its horizontal and vertical projections. These are delta x and delta y. The cosine of theta is delta x divided by L, while the sine of theta is delta y divided by L. These two-direction cosines are what allow a two-dimensional global displacement to be projected onto the one-dimensional member axis. In two dimensions each node has two translational degrees of freedom. Therefore one truss member has 4 degrees of freedom, Ui, Vi, Uj and Vj. But the member itself can only stretch along one direction. So we need to combine these four global components into one axial deformation. Only the component of each global displacement along the member axis contributes to axial deformation. At node I, the projected displacement is c times ui plus s times vi. At node j, it is c times uj plus s times vj. The axial extension is the difference between these two projected displacements. After expansion, we obtain the key relation, one scalar axial deformation expressed in terms of four global degrees of freedom. The four coefficients in the expanded deformation equation can now be collected into one row vector. This is the B matrix. B multiplied by the element displacement vector gives the axial deformation. Divide by the element length and we obtain the strain displacement relation. This compact B matrix is the bridge between global nodal displacement and the one-dimensional mechanics of the truss member. Once B is known, we return to ordinary mechanics. The B matrix gives strain. Young's modulus converts strain into stress. Area converts stress into axial force. Combining these relations gives axial force equal to AE over L times B times the element displacement vector. The axial force acts along the member. But finite element equations are written using global nodal force components. The transpose of B transforms the scalar axial force back into the four global nodal force components. Substituting the expression for N gives the complete element force relation. We can now compare our result with the standard finite element relation, element force equals element stiffness times element displacement. Therefore, the two-dimensional truss element stiffness matrix is simply AE over L multiplied by B transpose B. This compact equation is the most important result of this tutorial. The 4x4 matrix will now come automatically from multiplying B transpose B. Now expand B transpose B. B is a 1x4 row vector, so its transpose is a 4x1 column vector. The matrix product is therefore a column multiplied by a row. For example, the first row comes from minus c multiplied by every term in B. Repeating the same multiplication for all four rows gives the complete matrix. This is exactly the matrix we used at the beginning. We have now derived every one of its terms. Let us evaluate the matrix numerically. Take a member with a horizontal projection of 2 meters and a vertical projection of 1.5 meters. The length is 2.5 meters. Let Young's modulus be 200 gigapascals and the cross-sectional area be 100 square millimeters. The direction cosines are 0.8 and 0.6. Substitution gives the numerical 4x4 element stiffness matrix shown here. The units are newtons per meter. The matrix entries also have a physical meaning. The c-squared terms describe the contribution associated with the global x direction. The s-squared terms describe the corresponding contribution in the global y direction. The cs terms are the coupling terms. They appear because an inclined member does not align with either global axis. Horizontal and vertical motion can both contribute to axial deformation. A good finite element formulation should pass simple physical checks. For a horizontal member, theta is 0, c is 1 and s is 0. The matrix therefore reduces to the familiar one-dimensional axial behavior in the horizontal direction. For a vertical member, theta is 90 degrees, c is 0 and s is 1. The stiffness contribution moves to the vertical direction. Finally, the stiffness matrix is symmetric. This is an important property of the linear elastic element formulation. Let's put the complete derivation together. We started with global nodal displacement and projected it onto the member axis. Dividing by length gives strain, and Hooke's law gives stress. Multiplying stress by area gives axial force, and B transpose converts that axial force back into global nodal components. Comparing the result with the standard finite element equation gives the compact stiffness expression. Expanding B transpose B produces the familiar 4x4 matrix. This is the complete derivation from basic mechanics to finite element formulation. The key lesson from this episode is not the 4x4 matrix itself. It is the derivation behind it. Once you understand that the stiffness matrix comes from AE over L times B transpose B, the formulation becomes systematic rather than something you have to memorize. In the next episode, we will take these individual element matrices and assemble them into one global stiffness matrix for the complete truss. That is where individual finite elements become one structural system. In the previous tutorial, we derived the stiffness matrix of a single two-dimensional truss element. But our structure contains three members. So the next question is, how do their three-element matrices become one matrix for the entire structure? Before assembling anything, we must establish one global degree of freedom numbering system for the entire structure. Each node has 2 degrees of freedom, horizontal displacement U and vertical displacement V. With 3 nodes, there are 6 global degrees of freedom. Now we begin the actual assembly. For element 1, the member connects node 1 to node 2. Its 4 local displacement positions correspond directly to global degrees of freedom 1, 2, 3, and 4. Element 2 connects node 1 to node 3. The first 2 local positions still map to degrees of freedom 1 and 2. But node 3 uses global degrees of freedom 5 and 6. Therefore the mapping is 1, 2, 5, 6. Finally, element 3 connects node 2 to node 3. Its local degrees of freedom map to global degrees of freedom 3, 4, 5, and 6. So our complete connectivity table is now clear. Element 1 maps to 1, 2, 3, 4. Element 2 maps to 1, 2, 5, 6. Element 3 maps to 3, 4, 5, 6. We now perform the assembly numerically. Start with element 1 and its 4x4 stiffness matrix. Its connectivity is 1, 2, 3, 4. Therefore each entry of the element matrix is placed into the corresponding row and column of the global matrix. At this stage, the global matrix contains only the contribution from element 1. Next we add element 2. Its global degree of freedom mapping is 1, 2, 5, 6. Notice what happens. The element matrix does not occupy a new 4x4 block at the bottom of the matrix. Instead, its entries are placed at rows and columns 1, 2, 5, and 6. Where element 2 overlaps with the existing contribution from element 1, the values are added. Finally, add element 3. Its connectivity is 3, 4, 5, and 6. Again, its 4x4 matrix is scattered into the appropriate rows and columns of the 6x6 matrix. After this final addition, every member contribution has been included. We now have the complete structural stiffness matrix. Here is the completed global stiffness matrix. It is 6x6 because our structure has 6 global displacement degrees of freedom. Every number in this matrix has a physical origin. It comes from one or more truss members connected to the corresponding degrees of freedom. The most important idea in assembly is that overlapping entries are added, not replaced. For example, global entry K11 receives a contribution from element 1 and another contribution from element 2. Adding those two contributions gives 13.414 times 10 to the 6 newtons per meter. Before moving on, we should perform a basic matrix check. For this linear elastic truss, the assembled stiffness matrix must be symmetric. For example, entry K12 equals K21. The same symmetry appears throughout the matrix. The purpose of assembly is now clear. The three-element matrices have become one structural stiffness matrix. That matrix is now ready to enter the global finite element equation Ku equals F, together with the global displacement in force vectors. But we cannot solve this equation yet, because some of the displacements are fixed by the supports. In the previous tutorial, we assembled the complete 6 by 6 global stiffness matrix. But the matrix itself does not give us the displacements. We still need to apply the support conditions and solve the finite element system. Let us begin from the exact result of tutorial 5, the assembled 6 by 6 global stiffness matrix. It acts on the 6 global displacement degrees of freedom and produces the global force vector. Now look at the physical supports. Node 1 is a pin, so it cannot move horizontally or vertically. Node 2 is a roller. It cannot move vertically, but it is free to move horizontally. We can now divide the 6 degrees of freedom into two groups. The constrained, or prescribed, degrees of freedom are U1, V1, and V2. All three are 0. The remaining unknown degrees of freedom are U2, U3, and V3. These are the quantities we must solve for. Instead of modifying the physics of the structure, we partition the global equation into free and constrained degrees of freedom. The letter F denotes free degrees of freedom, while C denotes constrained degrees of freedom. Because all prescribed displacements are 0 in this example, the unknown part reduces to a smaller system involving only the free degrees of freedom. For our 3-node truss, extracting the free degrees of freedom gives a 3 by 3 stiffness matrix. The unknown vector contains U2, U3, and V3. The corresponding force vector contains 0, 0, and minus 10,000 newtons. We now have an ordinary system of 3 simultaneous linear equations. In matrix notation, the unknown displacement vector is obtained by solving KFF inverse multiplied by FF. Solving the reduced system gives the 3 unknown nodal displacements. Node 2 moves 0.3333 mm horizontally. Node 3 moves 0.1667 mm horizontally and 0.7621 mm downward. The 3 solved values are only part of the global displacement vector. We now place them back into their original global positions. The constrained degrees of freedom remain exactly 0. The complete vector therefore contains all 6 displacements. Once the displacement vector is known, the support reactions can be recovered from the original full system. The horizontal reaction at node 1 is 0. The 2 vertical reactions are 5 kilonewtons each. These reactions are not additional assumptions. They are calculated from the solved displacement field. We should never accept a numerical FEA result without a basic verification. The 2 upward reactions sum to 10 kilonewtons, exactly balancing the applied 10 kilonewton downward load. The complete solution workflow is now visible. We assemble the stiffness matrix, apply constraints, reduce the system, solve the unknown displacements, reconstruct the full vector, and verify equilibrium. The most important equation for this step is the reduced system KFFUF equals FF. This is where the physical support conditions enter the numerical FEA solution. In the next tutorial, we will use the solved displacements to calculate strain, stress, member forces, and reaction forces in a physically meaningful way. We have solved for the nodal displacements. But displacement is not the final engineering quantity. We now convert those displacements into member deformation, strain, stress, and axial force. We will also recover the support reactions. Our starting point is the displacement vector obtained in tutorial 6. The restrained degrees of freedom are 0. The free nodes contain the solved displacement values. For each truss member, we first find its change in length. For an inclined member, the global nodal displacements are projected onto the member axis. For element 2, the direction cosines are obtained from its geometry. Substituting the solved nodal displacements gives a negative deformation. Strain measures deformation relative to the original member length. For element 2, divide its axial shortening by its original length of 1.8028 meters. For a linear elastic truss member, stress follows directly from Hooke's law. Stress equals Young's modulus times strain. Using 200 gigapascals and the calculated negative strain gives approximately minus 60.09 megapascals. Once stress is known, multiply it by the cross-sectional area to obtain the axial force carried by the member. For element 2, the result is approximately minus 6.009 kilonewtons. Repeating the calculation for all three members gives the complete member response. Element 1 is in tension at 3.333 kilonewtons. Elements 2 and 3 are each in compression at approximately 6.01 kilonewtons. The support reactions are recovered from the original global equation after the displacement solution is known. The horizontal reaction at node 1 is 0. The two vertical reactions are 5 kilonewtons each. A simple and powerful check is global force equilibrium. The two vertical reactions must balance the applied load. 5 plus 5 minus 10 equals 0. The structure is in vertical equilibrium. We can also check the loaded node 3. The two inclined member forces must balance the 10 kilonewton downward load. The horizontal components cancel and the vertical components balance the applied load. Both equilibrium equations are satisfied. We can now summarize the complete structural response. The bottom member is in tension, the two inclined members are in compression, and the support reactions are 5 kilonewtons each. We have completed the post-processing stage. The finite element solution gives nodal displacements, and those displacements give member deformation, strain, stress, and axial force. The important point is that stress and force were calculated directly from the displacement solution, geometry, and material properties. In the next tutorial, we will combine these ideas into a complete reusable two-dimensional truss finite element solver. We have reached the final tutorial in this 8-part introduction to structural finite element analysis. Everything we learned separately is now combined into one reusable two-dimensional truss solver. First, the solver needs a model. We define the node coordinates, the element connectivity, material properties, cross-sectional area, and external loads. Next, the solver assigns two global degrees of freedom to every node, horizontal displacement U and vertical displacement V. This simple numbering rule lets the program translate element node numbers into positions inside the global matrix. For every truss member, the solver calculates its length and direction cosines and constructs the 4x4 element stiffness matrix. The same element routine can be reused for every member. That is one of the key advantages of writing the solver as a sequence of small functions. The element matrices are then assembled into one global 6x6 stiffness matrix. The important programming operation is addition. When two elements share a global degree of freedom, their stiffness contributions are added. The supports prescribe 3 displacement degrees of freedom. The global system is partitioned into free and constrained degrees of freedom. Because the prescribed displacements are 0, the unknown part becomes the reduced system. The reduced matrix equation is solved numerically using a linear system solver. The resulting free node displacements are 0.3333, 0.1667, and minus 0.7621 millimeters. After solving the displacements, the support reactions are recovered from the original full global equation. The two vertical reactions are 5 kilonewtons each, and the horizontal reaction is 0. The solver is not complete until the nodal solution is converted into physical member response. For this truss, the bottom member carries 3.333 kilonewtons in tension, while the two inclined members carry approximately 6.009 kilonewtons each in compression. A complete engineering solver must also verify its result. We check stiffness matrix symmetry and global force equilibrium. For this model, the numerical errors are essentially 0. The real achievement is not solving one truss. It is separating the program into reusable functions. The same algorithm can accept a different geometry, different connectivity, different loads, or different material and section properties. Let us put the entire process together one final time. We started with geometry and ended with verified structural response. That is the core computational workflow of a two-dimensional truss finite element solver.